In 2001, the mean rate of inmates on death row was 40.7 years, according to data by the U.S. Department of Justice. A sociologist wondered if the mean age has decreased since then. She randomly selects 32 inmates who have a mean age of 38.9 and a standard deviation of 9.6. Tests the claim at the alpha equals 0.05 level of significance. So what type of test is this? Do you see a percent or do you see the word mean? It's a mean. That tells us our hypothesis statements are about the mean, the population mean. In 2001, the mean was equal to 40.7, but our sociologist thinks it is less than 40.7, so that's her claim. And she is testing at the alpha equals 0.05 level. What is the sample data information? It's about a mean. So we need the sample mean, the sample standard deviation, and the sample size. She randomly selects 32 inmates, there's my sample size, who have a mean age of 38.9, sample mean, and a standard deviation of 9.6. Drawing the distribution, we're looking at the mu sub x bar is equal to 40.7. Our mean is 38.9. So that's our x bar. And our p-value is the shaded area to the left. We have a left tail. So we're looking at the probability that x bar could be as low or lower than 38.9. And that's our p-value. And is that less than alpha equals 0.05? The further away that x bar is, the smaller the p-value is going to be. So that's why we want it to be as far away as possible, to get a small p-value that will be less than alpha. Example 3. A bank claims that the mean waiting time in line is less than 1.9 minutes. A random sample of 20 customers has a mean of 1.7 minutes with a standard deviation of 0.8 minute. If alpha equals 0.05, test the bank's claim. Step 1, mean or proportion?
Mean.
Mean. What are the null and alternative hypothesis and the alpha? So we know it's about the mean. We're told that the mean waiting time is less than 1.9 minutes. So that's what we're looking at. Is it not 1.9 or is it less than 1.9? So it's worded a little differently. And our alpha is 0.05. Our sample data about the mean is 20 for our sample size, a mean of 1.7 minutes, and a standard deviation of 0.8 minutes. So our graph of the sampling distribution has our mean sub x bar is equal to 1.9, but our data has an x bar of 1.7. And we shade our p-value. So a left-tailed test. We're looking at the probability that x bar would be less than or equal to 1.7. This is our p-value. Is that less than alpha equals 0.05? Is it getting repetitive yet? That means it's good. All right, let's go on to number 4. The mean score on the Math MCAS grade 10 was 515 in 2000. An educational researcher claims that students who study algebra in the 5th grade have higher scores. He obtains a random sample of 40 students from schools who have students do algebra in the 5th grade and finds that their mean score is 540 with a standard deviation of 90. He wishes to test the claim at the alpha equals 0.05 level. So our test is about a mean. Mean was equal to 515, but with algebra, he thinks it's going to be a higher score than 515. And our alpha is 0.05. Now we get our data. He has a random sample of 40 students, sample size, a mean of 540, and a standard deviation of 90. So our distribution looks like mu sub x bar is equal to 515. We have a sample x bar that's 540, and that shades our p-value. So we're looking at the probability that x bar would be greater than or equal to 540, and that's our p-value. Is this less than alpha equals 0.05? Are there any questions? Okay, got 2 left. Example 5. According to a 2010 survey, the mean number of apps downloaded by iPhone users is 40. Suppose a sample of 36 iPhone users downloaded an average of 45 apps, and the sample standard deviation was 24. Test whether the population mean number of apps has changed using alpha equals 0.10. So we're talking about the mean. And our 2010 survey said we had 40. And now they're asking us to test whether the number of apps has changed. So we're going to use not equal to 40 here, because we are looking at whether they're larger or smaller when we take our sample. And our alpha here is 0.10. Okay, so this time we're looking at a mu sub x bar is equal to 40. Oh, let me get my sample data. I forgot to do that. So sample mean data. Our sample mean was 36 iPhone users for our sample size. Our mean was 45, and our standard deviation was 24. Now, in this case, we're going to have a two-tailed test, so we might have data on one side or the other. We don't know. But we were given a mean of 45. And that's giving us a p-value here. So this is our x bar for our p-value. So our probability is about x bar being greater than 45 in this situation. And that's our p-value. In this case, we're looking to see how it compares to alpha over 2 because we have the two sides test. So is that less than alpha over 2? And we do that because it's a two-tailed test. The two-tailed test you're not going to see a lot of, so you don't have to freak out about it. Remembering it's not a big deal. But I did want to show it to you in one example, two examples. One more example. The National Institute on Alcohol Abuse and Alcoholism reported that 46.5% of eighth graders had used alcohol. A random sample of 100 eighth graders showed that 41 of them had used alcohol. Is there evidence that the population proportion has changed? Tested at the alpha equals 0.01 level. So it's another one with a change, so a two-sided test. We have a proportion in this case because we have a percent. So we have P for both of our hypotheses. The first is that it's 46.5%, which is 0.465. And they just wonder about change, so it's a not equal to 0.465 with alpha equals 0.01. Our proportion, they told us that was 41 out of 100 students that were surveyed. This is going to give us a p-hat of 0.41. So we're going to be looking at our mu sub p-hat, which was 0.465. So our 0.41 falls over here on the left. And we do have a two-tailed test. Because of the not equal to. So our probability is the probability that p-hat is as small or smaller than 0.41. That's our p-value. And in this case, we want it to be less than alpha over 2 because it's a two-tailed test.